All right, welcome back for part 2 of our lesson for 10-2. Here's your bell ringer going over one of the types of problems we looked at in the first video. All right, so first step on this is to break down 27. So that's 9 times 3. 9 is 3 times 3. So there's your pair of 3s, and there's a 3 by itself, which goes in your box. So we're going to start off our answer, I'll just write down here, start off our answer with a 3 because of the pair. Then I look at x to the third power. If I have 3 x's, I could put 2 of them in a pair together. So there's one pair, right? First 2 make a pair, but there's only one pair. So we're going to have an x on the outside, and then that third x up there, since it was x to the third, is going to be by itself. We're going to have to put that one inside. Then, get rid of that. Then we got to look at y to the 8th. If I have 8 y's, that means I basically have 4 pairs of them, right? First 2, second 2, third 2, last 2. So y to the 4th. And there's nobody left alone in that case. Everybody paired up with somebody. And then z squared, that's just one pair of z's. Nobody left alone there, so we have a z on the outside there. That's everything on the outside. And then on the inside, first we're going to write our 3 that we had in that box. And then we're going to write our x, right? Just that one x from that group of 3 that got left by itself. So that would be your answer to this bell ringer. All right, hopefully that sounded good to you. Looking now at the rest of 10-2. So first thing we're going to look at is this quotient property. So basically the quotient property says, as you see right here, if you're taking the square root of a fraction, just a over b in general, that's the same as taking the square root of the numerator and the square root of the denominator separately. So you're allowed to do that, okay? The other thing we have to be careful about on these, and this is one thing we're going to see as we start working through these problems, we do not want to have a square root in our denominator for our answer. Okay, that's not going to be considered a fully simplified answer. So we're going to have to talk about a way to fix that. So let's see, yeah. So that'll happen here, right? So the square root of 3n over the square root of 8. So I want to consider each of those separately. If I think about the square root of 3n, now I can come off to the side if I need to and think this up. But if I think about 3 can't really go anywhere. It's prime already, just 3 times itself, or 1 times itself. And since there's only one n, I can't really do anything with that either. I can't bring anything outside. So the 3n, that's just as simplified as it can be right now up there. Now if I think about the square root of 8, so I'm just going to get rid of that. We didn't use it anyway. Square root of 8 is 4 times 2. 4 is 2 times 2, so we have a pair, and then we have the 1 by itself. So this would be my first step. I would say that this is the square root of 3n, because that didn't change, over 2 square root 2, right? That 2 went on the outside, and this 2 went on the inside. So that was from yesterday's lesson. Okay, so good. That's more simplified than it was initially. But now comes that problem I mentioned on the previous slide. We do not want to have this square root in our denominator. Right? Just one of the rules of math. Can't have a square root in the denominator. So how do we fix that? The way to fix it is to multiply by that square root over itself. So since we had a square root of 2 and we don't want it, we're going to multiply by square root of 2 over square root of 2. Okay, so let me just get that out of the way so you can see what you're looking at. So that's the way we're going to fix this. And you'll see in a second why it fixes it. So in the numerator, we're looking at square root of 3n times the square root of 2. All we have to do there is multiply the two things we have under radicals. In other words, we're going to multiply 3n times 2. So what's 3n times 2? Should be thinking that that's 6n. And since both of them were under a radical to begin with, we're going to keep it under a radical. It's kind of a weird looking radical. So that's the square root of 6n. That's what we now have in our numerator. How about the denominator? 2 square root 2 times square root 2. This 2 is going to stay, okay? Because what I always say is you always multiply numbers that are on the outside of the radicals, and you multiply numbers that are on the inside of the radicals. So because this does not have another number on the outside of its radical, right? This doesn't have like a 5 here or anything like that. This first 2 has nobody to pair up with, right? So that 2 just stays. The radicals, however, we have a square root of 2 times the square root of 2. We're going to multiply those. 2 times 2 is 4. If they started under the radical, we're going to keep them under the radical. So that's square root of 4. Now you might be thinking to yourself, well, what good did that do? We still have a radical down there. The good that it did us is now we have what we call a perfect square under our radical. If I look at the square root of 4, you should know the square root of 4, right? What is the square root of 4? What number times itself gives us 4? 2. We actually know that because that's how we got the 4. We multiplied 2 times 2. So this gets simplified. Square root of 6n is not changing. But on the bottom, we're really saying that this is 2 times 2. It's this 2 times the square root of 4, which is 2. And now our last step is going to be to say that this is the square root of 6n over 4. That is your final answer. You might be sitting there thinking to yourself, well, if I have 6 over 4, if you're looking at these two numbers, can't I reduce that fraction? The answer is no, because the 6 is under the radical. Okay, if that 6 is under a radical, it's not technically a 6. It's the square root of 6, which is some weird number. It's 2 point something. Okay, so that would be your final answer here. All right, sure that probably felt a little bit confusing. Oh, it says D, but it was multiple choice. Okay, whatever, trust me. So let's look at another one. All right, same thing on this one. If I look at the numerator, square root of 2, can't do anything with square root of 2. That's already as simplified as it can be. If I look at square root of 27, though, in the denominator, I could say that's 9 times 3. 9 is 3 times 3, so there's a pair. There's one left alone. So there's our first step. We're going to say that this is the square root of 2, which did not change, over 3 square root 3. Right? There's your first step. Now we do not like the square root 3, so here's where we're going to multiply by root 3 over root 3. Okay. The numerator is just the square root of 2 times the square root of 3. That would be the square root of 6. 2 times 3, 6. And in the denominator, again, this 3 is just going to have to stay out front. It doesn't have anything else to multiply with. And then we have square root of 3 times square root of 3, which is square root of 9. So we have square root of 6 over, the 3 is not changing. We know the square root of 9, hopefully. That's 3. So 3 times 3 in the denominator. So this is square root of 6 over 3 times 3 is 9. There's your answer. Now you might be picking up on a little shortcut here. Okay, so hopefully you have all that. Let me get rid of this. I'm just going to use this slide to show you a little shortcut. If I have, I'm just going to make up, let's do some crazy numbers. Let's say square root of 75 times square root of 75. Okay, now it's square root of 75. If I wanted to do a factor tree on it, I could. It's 25 times 3, and then 25 gets broken down into 2 5, so it's 5 root 3 for the record. But my point is, any square root times itself is just the number that is under the square root, 75 in this case, right? If I have square root of 29 times square root of 29, that's just 29. And the reason I'm showing you this is, like on the previous example, we had square root of 3 times square root of 3. If you want, you could say that's square root of 9 and then say that's 3. But if you compare it to those two previous examples that I just did here, you're seeing that you can go right from here to saying, oh, okay, that's 3 because it's a square root times itself. So that's not something you have to use, but you might find that useful. All right, one last thing to look at here. Okay, this is what we call multiplying by the conjugate. You see the word, see the word conjugate here, conjugate. And we call it rationalizing the denominator. So again, we don't like this square root of 5 down here. So when I initially look at this problem, I'm saying, all right, I don't like that radical in the denominator, but I can't really simplify it at all right off the bat. 5 is a prime number, so I can't simplify that radical. I can't really do anything here, right? So we have this trick, which is called multiplying by the conjugate. So we're going to multiply by, since I have a 4 minus root 5 down here, we're going to multiply by 4 plus root 5 over 4 plus root 5. You change the sign. That was a minus, so we're going plus. Okay. Now, what happens from here? The numerator is pretty easy. All we got to do, this is basically in parentheses, we're distributing this 2. Okay, so 2 times 4 gives us 8. And then 2 times root 5 is not root 10, because this 2 is not under a radical. And that 5 is, which means all we can say is that was plus, so we're gonna keep the plus. 2 times root 5 is 2 root 5. We cannot multiply those numbers together if one of them is not under a radical and one of them is. So please keep that in mind. In the denominator, it's a little bit different. We have 4 minus root 5 right there times 4 plus root 5. So how the heck do we multiply those? You're really going to want to go to your box method here. Okay, you're going to want to jump back to your box method. So let's make a little 2x2 box. I'm going to have 4 minus root 5 and 4 plus root 5. So you put a plus there if you want. And now we're going to do our box method. First box here is 4 times 4, 16. Second box is 4 times negative root 5. That would be negative 4 root 5. Again, 4 is not in the square root, 5 is, so I can't multiply 4 times 5 and say it's 20. Okay, I gotta say that's 4 on the outside, 5 in the inside of the radical, and then I just brought this negative out front, right? Then in the bottom left box, I'm looking at 4 times a plus root 5. That would just be 4 root 5. I don't have to write the plus out front, it's just positive. And then in my bottom right box, it's a positive times a negative, so that would be a negative. And then it's a root 5 times a root 5. So like I said on the previous example, it's a square root of 5 times another square root of 5. That's just going to be 5. If you want to go the longer route, you're going to say that that's a square root of 25, because 5 times 5 is 25. But the square root of 25 is 5. So it ends up being a 5 either way. Now what's going to happen every time on these is if we look at our diagonal here, these are always going to cancel each other out. They're always going to subtract out because it's always going to be one positive, one negative, but otherwise they're the same thing. They're both a 4 root 5, but the one down here is positive, the one up here is negative. So those go away. And now all we're looking at is we actually just have 16 minus 5. Well, 16 minus 5 is 11. So we just have 11 down there. So you probably never would have guessed that those two things would have multiplied just to the number 11, but that's what we get. So 8 plus 2 root 5 over 11. The only thing I want to look at now, so I'm just going to write this a little bit bigger down here. The only thing you want to look at from here is, can these three numbers be divided by anything? In other words, is there any number that goes into 8, 2, and 11? And the answer in this case is no, because 11 and 2 are both prime. So in that case, this would be your final answer. 8 plus 2 root 5 over 11. A little bit sloppy with the work and all, but it's basically just going back to box method there. Okay, let's look at another one here. All right, this one looks fairly similar. So again, our trick whenever we see this is we're going to multiply by the conjugate. 3 plus root 5 over 3 plus root 5. Right? The top we're distributing. 4 times 3 is 12. 4 times root 5 is just going to be plus 4 root 5. Because we got a plus there. And if it's 4 times root 5, we just got to keep it as 4 root 5. Denominator, we're going to go to our box method. So there's our box. We have 3 minus root 5, 3 plus root 5. All right, 3 times 3 is 9. Top right box is going to be negative 3 root 5. Bottom left is going to be positive 3 root 5. And again, you already see these are gone. One positive, one negative. They cancel. And then in this bottom box, again, it's just minus 5. Because it's a plus times a minus, which gives us a minus. And it's root 5 times root 5, which is just 5 itself. So all we're left with now is 9 minus 5. Well, 9 minus 5 is 4. So we have 4. So here's what I was talking about on the previous slide. So let me just make some space here. I'm going to write this a little bit bigger. 12 plus 4 root 5 over 4. Now when I look at these three numbers, you should be thinking, what can I divide all those by? Well, I can divide them by 2, but there's an even bigger number, which some of you might be able to see there, right? I can divide all of them by 4. So I need to do that, or else my answer is not fully simplified. So I'm just going to rewrite my answer, but I'm dividing all those numbers by 4. 12 divided by 4 is 3. 4 divided by 4 is 1. So I could write the 1, or I don't have to. I'm just not going to write it. The square root of 5 doesn't change. Okay, because again, we can't mix numbers on the outside of a radical with numbers on the inside. So the fact that we're dividing these by 4 has nothing to do with that square root of 5. That stays. And then 4 divided by 4 in the denominator is just 1, which means don't even need to write it. There's our answer. 3 plus square root of 5. Right? Because it was that over 1, which means it's just that, basically. Multiplying by the conjugate. 3 plus square root of 5. All right, so this might be a lesson where you go back and watch it. I know it's a little bit confusing there with the conjugate and all that, and going back to your box method. So be careful. You could still, for the record, I'll throw this out there. On these problems, I could still type this into the calculator, the original problem. Do a little alpha y equals 4 over 3 minus root 5. See what you get there. Then if you get to 3 plus square root of 5 as an answer and you type that in, you're going to get the same decimals for both of those. Right? Whereas if you had something else, you would not be getting the same decimal, so that would tell you you're wrong. So that's a way you could check there. All right. Homework assignment for tonight is right there. Okay. And going back to the huddle, you're just going to do these last 4, 7 and 10. So pause the video, give those a try. And all right, the answers are, if I can read my handwriting, 7 is 2 square root 5h all over 5. So 2 root 5h with a 5 in the denominator. 8 is 2 root 3 over b. 9 is 8 minus 2 root 5 over 11. And 10 is 6 plus 3 root 3. And as always, okay, people have not really been doing this, but if you tried out those huddle problems and you did not get the answers that I just read off, you might want to send me an email. If you're doing this before Wednesday or on Wednesday, you might want to say, can we do a Zoom so I can get caught up on this, or you can help me out a little bit. Okay. Otherwise, mastery's there. Numbers 4 and 5. Okay. And then again, there's your homework. That's all I have for you this week. Let me know if you need help. Hope everybody's doing well.